Hey guys, everyone, thanks so much for joining. We're really excited to present this use case and study that came out of Central Hudson. My name is Ryan Chatel. I'm the Senior Product Manager for Sensus, and I'm going to introduce Ryan Yakush and Kevin Post from Central Hudson. Kevin Post is the Smart Grid team leader for the engineering side, and then Ryan Yakush is an engineer at Central Hudson. So what you're going to see today is a cool, creative, innovative way to manage the DER on their system. And it is, I won't spoil it, but there are some really cool insights that you're going to see. So Ryan and Kevin, I'm going to hand it over to you.
Kevin, I think you're on mute still.
There we go. All right, can you hear me now?
Yep.
So I'm Kevin Post here with Central Hudson. Central Hudson is a IOU, part of the Fortis Federation, located here in New York. We stretch from the suburbs of New York City to the suburbs of Albany. Got about 300,000 electric customers there, 2,600 square miles of service territory. And as of roughly right now, we got about 10,000 DER sites that are interconnected, most of them being rooftop solar, totaling up to about 200 megawatts of capacity. We've got another 200 megawatts in the queue for potential installation, most of those being solar farms, large-scale solar farms. We've seen an increase in that in the past couple of years. Next slide, please. All right, so our problem area is this 69 kV transmission loop up in the northwest portion of our service territory. It's about 40 some odd miles in length, and loop is a rough term. It is two lines that are operated radially and have a normally open breaker tying them together. There's lots of empty land in this area, so we have seen a large increase in solar farms that have been sited into this area recently. Next slide, please. And as you can see, these are where some of the large solar farms have ended up at these different substations here. In total, this is about 20 megawatts of generation, in addition to the native customer load, the rooftop that's already out there. So this was a rapid increase of 20 megawatts of generation onto this line. Next slide. So the problem that occurs with this line is this bulk amount of generation in this one spot is if the line gets, we have any switching that occurs and we have an outage and the line configuration changes, we can end up with over voltages on the transmission system. So, you know, it's not something that's going to occur regularly, but it is a risk. So in order to mitigate that risk, we would have to do something to be able to take these sites out when the line is in abnormal configuration, or not allow them to come online. Not allowing them to come online isn't really a feasible option. So then it's how do we accommodate them to deal with these deal with the risk of abnormal conditions. The old school way, traditional way, was, you know, it's a hardwired DTT solution. You know, you run you get a copper line from the phone company, and you have a copper line going from substation to site, and then you use direct transfer tripping schemes, and you link the circuit breaker at the substation to the customer site breaker, and you send signals and automatically trip it off. Okay, that's easy that's easy to do for a simple situation. Well, here with this loop, you've got multiple sites, multiple breakers, multiple configurations. It would be very complicated to program a conventional system to handle all of the possible configurations of this loop, and to add on additional sites. Very complicated. So, and very costly. And the goal in New York is to ease the burden for any sites to facilitate the adoption of more distributed generation. Next slide, please. So again, here's the conventional solution. Phone line microwave, fiber, power line carrier. You know, that's the conventional solution, and it's really a point-to-point. Well, when you have multiple source points and multiple destination points, a point-to-point system kind of has some problems. So next slide. This is the installation we did. We did one traditional installation. This was the DTT box at the DER site. That box is 5 foot tall, 3 feet deep, 3 feet wide. Decent sized thing that went on a pole, and this ties into an electronic recloser that provides the tripping for the site. As you can see, quite a bit of chunk of change here to make this, you know, to put this solution in, and you know, the developers of the solar side have to pay for this, so it greatly increases their cost and reduces the feasibility of their site. But with that, I'll turn it over to Ryan. He'll talk about what we came up with Sensus.
Hey, thanks, Kevin. You hear me all right? Perfect. So, yep, that brings us to our proposed solution here, which we say proposed, but really at this point, it's running live. It's an implemented solution. So this is just kind of an overview here to show that this solution really takes us all the way from our EMS system out to the field through some Sensus equipment, then through the Sensus servers, and then back down to the solar farms, which could be located anywhere, just as Kevin said. Just an important thing to note here, you'll see at the top, it is one-way flow through that beginning portion, and I'll get into that as to why that's important here in a little bit. Next slide. So the first part of this solution really had to happen in our EMS system. As Kevin said, overvoltage is an issue, and it's something that we need to be aware of when these contingencies happen. Breakers open, we lose transmissions lines or whatnot. So we worked with our protection and transmission planning group to identify which breakers opening or line loss would result in these overvoltages and what corresponding PV sites need to trip off to ensure that we're maintaining that reliability and voltage stability. So can't really see here, but in the logic table, there's a bunch of different case numbers assigned, and each of those correlates to a specific breaker or transmission line issue, and then identifies which PVs need to trip. And then that is transitioned to a 6-bit command that would go out when there's an issue. Additionally, we programmed in a manual reset. So this is controllable by the operator. So once a condition is cleared, they're the only people that can restore the sites back online that have been tripped. And that's just to ensure that our system's back to normal and we don't have any voltage issues. Next slide. So this is running in real time. It's monitoring our EMS system, and when something happens, it triggers a command, logic that's been programmed in our EMS system. So when something's identified and that logic trips, initiates an output to one of our substations to a Axion that's in the field, and this is connected directly into a Sensus micro RTU. It uses 6 binary inputs, and it's a hard connection into those. 6 bits allows us 64 different combinations, which is really beneficial because we're only using a handful of those now for this transmission loop. So it's going to be really expandable if we have another issue in a different area where solar starts to pick up, or we come up with more solutions for this. So leaving us a little bit of future-proof. So this is where I had mentioned the one-way flow. This was super important to us, just in case there's any issue with cellular. You always hear it's a little less secure, so we wanted to make sure that there's any issues on cellular networks that it couldn't get back to our EMS system. So because the micro RTU offers some dry contacts to connect into, there's no way to get from the micro RTU back up into your EMS system, and that's really giving us a lot more security. This RTU is installed in one of our substations, but really you could put it anywhere you have service. So next slide. Next slide.
Go back.
Sure. Yeah. So this really brings us to the brains of all this and what's really controlling those solar connection points out in the field. This is Sensus's automation control, and this is just a little snip of a very small portion of automation control. It's super powerful. This is what we leverage to make this solution possible. So what you see on the screen here is what's called control action routines. So these are programmable if-then statements that you can write, super customizable, use different inputs, different outputs, and it just gives you a lot of flexibility for the solutions that you're looking for. So what we did is we monitor that the TH66 micro RTU for those 6 inputs, and we wrote some if-then statements that look at those 6 inputs and then initiate a sequence of outputs based on what it receives. So if breaker A trips, then we know we need to trip sites 1, 2, and 3. So each one of those are written into here and give us that option to trip all these, and it all works simultaneously. When the conditions are met, each one of them fires and then trips off the PV sites, and then we wait for that reset to bring them back online. Very scalable. Each one of these commands, once you're familiar with them to write them, takes less than 10 minutes. So as more PV sites come online and they start to be in all different locations and different areas, it's really easy to just write a new one of these scripts, look at those inputs, and it goes right to the output of our reclosers. It communicates to an RTM too, which is inside the reclosers, and that's standard equipment for us. It comes installed in each of them. So it was kind of a no-brainer, really easy to implement solution, just needed that TH66 and then it could flow from there. One of the things I had mentioned was the one-way flow. Where this comes into play is because it is only one way, we don't get feedback into our EMS to know that the command has been received. And that's something you do gain with a traditional DTT scheme, with a hard line, with a sound that you have that monitoring. And we wanted to make sure that when those commands were sent out, the sites did trip, and we knew that that was going to be online all the times in case there's any hiccups in cell signal or whatnot. So that led us to create a sort of heartbeat feature that Kevin's going to get into now on the next slide.
Thank you. So as Ryan kind of alluded to, we've been using we use the Sensus RTM product. We've been using that for many years. That goes in every one of our distribution automation devices, and that we use that for monitoring of the sites, making sure the status is good, everything's working, and then monitoring all the analogs, voltage, current, so on and so forth. And then we also have control over the devices, and so it's something we've been using for years. So very comfortable with the Sensus product, and so then we learned about the TH66 and was able to expand upon it with minimal extra effort. It was just a little engineering brain power to come up with these schemes, but it was something we were already very familiar with, a product we were very familiar with, and so we expanded upon it. So as Ryan talked about, doing this cellular system, it's autonomous, and then the parts don't necessarily know what each other is doing. So we wanted to make sure that it would be fail-safe. Sensus has been ridiculously reliable for us. I mean, it's just always there. But who knows? A couple planets might align, and it may be down for a couple hours one day. So just in case, if the inevitable actually happens, we need to set up some backup. So what we did is we use Schweitzer 651R controllers for our electronic reclosers. And what we did in there is we created 2 timers. And when we start up a new site, we have to give it a little quick kickstart, and we start up a timer, and that's that point number 52 there. And so we start the timer and set the point to 1. And in 5 minutes, that point will change from 1 to a 0. Sensus is constantly watching the device, and it'll see that point change to 0. We have a control action that's set up, and when it sees it set to 0, it sends a pulse, resets that point back to 1. And that occurs every 5 minutes, every day, and it's been doing it since the system went online in November. Every 5 minutes, constantly sending a pulse. Well, for some reason, if we have a hiccup in cell, Sensus is down, the RTM fails, anything happens, that 0 won't get reset back to 1. And at that point, a second timer will start, which is point number 53, and that will watch for 10 minutes. And if point 52 hasn't changed to a 1, point 53 will then initiate and go to a 1, which is in the trip equation, and will trip out the recloser. And so if we lose the RTM, if we lose the website, we lose cell signal without, after 15 minutes of no communication, that site will trip offline. And then as an additional level, the T866, which is monitoring this whole scheme on this transmission loop, we also have a signal that'll come from the Sensus is monitoring all the devices as well, and they can go, they're online or offline or missing if they happen to go out. And so if that T866 should have a communication issue, point number 45 there, we'll get a pulse from the website, and that will trip it as well. And then we split up all of our different trip conditions. We kind of geeked out on it and took advantage of all the functionality in the 651, and we split up all kinds of trip conditions, so that way when a site does trip out, we know exactly why it tripped out, and can reduce truck rolls, and then we also have different reclosing conditions for some of the events. It's okay for it to go back in. For others, we need to roll a truck. So we split it up, and then we also put this on the display, so when the crew shows up, they'll see the same. They'll see the same reasons for why it tripped out. Next slide. So again, kind of a reiteration of the solution that we're doing. So that the SCADA EMS signal, or SCADA, the EMS system, it will be monitoring the transmission system, looking for abnormalities. It sends it out to an RTU there in the substation. The RTU sends it to the T866, this micro RTU, which is and just to also a little clarity, the Axion is sending it out on digital outputs, and Sensus is digital inputs. So there is no possibility for going backwards. Inputs can't become outputs, and outputs can't become inputs. So it ensures that nothing could go backwards and get into our EMS system. So from there, Sensus goes up to their server, and their server has the automation control and the control action routine logic that is running all the time, and looks at the conditions that come from the T866 and makes the decisions that goes out to the reclosers and trip the sites or bring them back online. Very reliable system. Like I said, it's been rocking since November of last year, and every 5 minutes we get that pulse, and constantly working. And during this summer, we've actually had 2 instances where something happened on the transmission loop, and perfect. It worked exactly as planned. Whole lot of emails. We set up. The great thing with Sensus is we also have emailing and texting capability for all kinds of points. So until we had the first live event, I was monitoring all the devices with all the points, and got a whole lot of emails and texts all at once. But it was kind of neat because I knew exactly what happened. I could see those emails and know, okay, that portion of the transmission line tripped out. Within minutes. I don't think our system operator had even figured out which portion of the transmission line it tripped, but I already knew, and I also knew that all the DER sites were offline as well. Great. We don't have to worry about any problem here. Next slide. So this is what the Sensus setup looks like out in the field as compared to that giant box. We got this little box side of the wall out of the way in a substation. The first one cost us a little bit of money, but that was all on engineering time. The Sensus box is very inexpensive. We extensively tested the solution. We have a recloser up in our lab here and a test set, and we tried to make it line department proof, and came up with the schemes and the heartbeat and all the logic, and thoroughly tested it out. That was significant amount of engineering time to figure out the first solution, but the hardware is very generous. So and then going forward, the per site costs are super minimal. Less than a day of engineering time, typically a heck of a lot less. Ryan said, I let him know, hey, we need to add a new one, and he has it added before he finishes his cup of coffee. and it's up and working, and it's good to go. Next slide. So again, costs, incredible difference in cost. We funded that first installation that was out of Central Hudson, and then the developers are paying these minimal costs for future sites that are going in, which reduces the barrier for them to get DERs on the grid. So next slide. So again, just kind of a conclusion of what this project did is it dramatically simplified implementation and allows us to scale DG as penetration is increasing. We're using existing equipment that we've been using in the field, and very comfortable with it, and we just took it to the next level. The communication that we get from the system helps us, reducing field labor maintenance. That big box had a lot of that big DTT box. The one we've had some issues, and actually the customer there may be switching over to the Sensus solution because we've had problems. Copper phone lines are not cool anymore, and they're not maintained, and they've had a lot of issues to that. And just learning about that big box that we made, we've had some issues there. So the one conventional system that we have may be going away. And as I mentioned, there's a net savings, for the company and the customers. It's the interconnecting customers reimburse the company for all of our costs, but they don't really reimburse us for the time. Yeah, they paid for our time to develop their solutions and get them interconnected, but I spent 2 weeks on it. It's 2 weeks I can't do on something else, and I'll never get that 2 weeks back. Even though they're paying for time, you don't get that time back to do other things. So being able to accomplish a mission in an hour is incredibly valuable. So then just some other things that we're doing. Ryan and I are playing around with this in other ways with some DER sites. So we have some DER sites that are between automatic load transfer schemes, and the sites are only studied to operate on the normal source. And if they get swapped over to the alternate source, they shouldn't be online. So we're going to use the same if-then logic, monitoring the status of the normal source. They get swapped over, trip them offline. And a big thing that my teammate here, Ryan's been involved with, is trying to maximize the use and the efficiency of switch capacitor banks that are going in with some of the DER sites. So some of the recent DER sites are not operating at Unity. They have to operate off Unity to mitigate other issues with their installation. So when they're going in, they have to purchase a switch capacitor bank, and the switch capacitor bank isn't necessarily in a place where it sees their load and will sees their generation. So you can't just operate it on VAR flow or load or voltage and get it to follow them. So we want to use Sensus and the automation control system to remotely monitor the load or the generation coming out of that DER site and kick on the switch capacitor bank. So that way you're not limited. You don't have to have that switch capacitor bank installed upstream from the DER site. It could be downstream, it could be wherever, and they'll be tied together. Sun comes up, switch cap goes in, sun, cloud goes by, switch cap opens up, and so allows them to follow each other. And we've had great luck with the system going anywhere. One of the sites where we put this at, I mentioned we use the cellular flavor of Sensus's product, and some people may have some limitations where cellular can be, and we actually have a limitation in one of the spots. One of the last installations, there is no cell signal. Your cell phone, it laughs at you. There is no signal. And we put up an antenna with a little bit higher gain and then a cell booster, and boom, we've got 4 bars. So to the average user, you would think there is no cell signal there. Well, when you toss on a little bit of you toss on a booster, and that's more than enough for Sensus, and it's rock solid. we're the only person in that area that has good cell service. Nobody else out there has good cell service, and that little extra didn't cost anything. It was minimal expenditure, and we're working in a spot where there is no cell signal. So
I think in summary, I just want to kind of wrap up and take a couple questions if we have time. But I think this highlights some of the innovative approaches that utilities are starting to take with real challenges in DER right now. No matter where a solar farm pops up on Central Hudson's grid, they've now created a solution that is scalable, cost-effective, and autonomous. Absolutely remarkable. So I think we'll take a couple of questions. Really, enough can't be said about Ryan, Yakush, and Kevin Post's ingenuity here and how you've applied, the really robust solution within automation control. So we'll see if there's any questions here. Looks like there's one.
There is one, but we're gonna have to get that to you guys later on since we're over time. But thank you guys. It's an extremely unique presentation. Sounds like you guys are doing a lot of great stuff there. So hopefully this gets pushed around to other utilities around the country. And thanks for joining everybody today. This session was recorded, so we're gonna potentially post this around for other people to view and see moving forward. So once again, thanks everybody for joining, and Kevin, Ryan, thanks for your time.
Thank you. Have a great one.
Today's session.